Assalamualaikum everyone. This is my OBE assignment for Digital Logic and Circuits course, and the task is to design an automated digital parking control system where the main objective of the system is to monitor how many cars are present inside a parking area and to display the parking status accordingly. So the maximum capacity of the parking system will be measured by our ID, and this will be done with this equation here, and which is b plus x plus h. So the system is basically constraint based and personalized here. So let's get into our assignment. So this is the answer for our first question. So at first, what I did first, so basically at first I analyzed the problem and divided the entire system into some smaller functional blocks. So this helped me clearly understand how the input signals move through the system and produce the final output. So basically the total space of the garage will be, for my case it will be 8, and we will need a 4-bit counter. More specifically, it will be a 4-bit synchronous up down counter, and we will talk about it later, why did we use an 4-bit synchronous counter. So as for now, we will move to our block diagram. And before going to the block diagram, I want to share something, and that is how the system starts. So basically the system starts with an entry and exit, where there are two sensors placed at the parking gate. Whenever a car enters the parking area, the entry sensors generates a digital pulse. Similarly, when a car exits, the sensor generates another pulse. The pulses act as input signals for the digital system. So now let's talk about our block diagram. So here we can see these two entry and exit sensors that we talked about earlier, and there are from there it was connected to a 4-bit counter that we talked about earlier, and the 4-bit counter was connected to a comparator, and this comparator actually compares the maximum value with the cars present inside. Then if the value is above 8, then it will show in that 7-second display that the garage is full, and if it's less than 8, then it will show the it will say space available while blinking the LED. And if we notice here, there will be an register connected to comparator, and above that there will be a keypad, and this keypad is used to give the input as the maximum space of the garage, which will be in my case 8. And then that decimal number will be encoded by the encoder, and then it will be stored in the register. Now if we go forward, then we will see our flow diagram. So this flow diagram actually represents our whole project, or maybe our system, which actually starts. Then we will give the input, which is in our case is 8. Then the encoder encodes, then it will be stored in the register. Then if there will be a condition where if the car enters, then it will increase the counter, and if there is no entry car, then there is a possibility that there might a car exit and there might not. So if the car exits, then it will decrease a count, and then the both results, the increment one and the decrement one, will be compared. And if the count is 8, then the 7-second display will show full, which will disable actually timer 2, which is in our case we used for blinking, and enable timer 1, which is for showing the text full. Then this whole process will be repeat after the car takes an entry or leaves. Okay, so now let's talk about our counter. So at first, why did I use a 4-bit synchronous up down counter, right? So it is used to keep the track of the number of the parked cars mainly, and I used this counter I use the 4-bit synchronous up-down counter. So the entry sensor provides the count up signal, and the exit sensor provides the count down signal. And since the counter is synchronous, all bits change at the same time, at the same clock edge, which ensures stable and glitch-free operation. Now, if we talk about the counter diagram, in the counter diagram, this block actually represents the 4-bit synchronous up-down counter. Internally, it is built using flip-flops, but I used the complete counter block to simplify the design, improve reliability. So my ID, the count was 8 for the maximum capacity according to my ID. So the garage can be either empty or it can hold cars up until to 8. So it can hold actually maximum 8 cars inside the garage. And when the entry sensor, the pulse according to entry sensor works, the count will increase and the U will be 1. And when the exit sensor works, then the U will be 0. This is actually the representation of this counter diagram, and we will use a 4-bit up-down synchronous PCD decade counter, and we will use the mod 9 for the system designing. And because of the reason for mod 9 is we will actually need 8 cars inside the garage to to cope up the maximum capacity. So it will be not 7, it will be 8, as we can hold a maximum 8 cars into the garage. Now let's talk about the state table, which I designed to get the equations and the block diagram. In the table, the current state represents the present binary values stored in the counter, and next state shows the value the counter will transition to after the next clock pulse. So this table confirms that the counter increments correctly for entry and decrements correctly for exit. In all valid states, it works. So the state table validates the correctness of both the counter design and the derived equations, which we'll be talking about later. As it was an up-down counter, so we can see here two states, mainly three states. This is the current state, and the next state either can be this one or this one. So basically, if we go up, then that will be the middle one, and if we go down, then that will be the right side one. So this is the state table. And for the block diagram, as usual, we used a JK flip-flop with the clock, common clock connected to the edge, and the high was this input taken high, then the Q0, Q1, Q2, and Q3 as the outputs, and the outputs from Q0 was connected to the as an input for Q1, then the Q1 as for Q2, and the Q2 as for Q3. So this way we designed the block diagram of the counter. Now let's talk about the equations. So I derived the logic equations to clearly define how the counter changes its state, basically, and these equations express the relationship between the current states of the 4-bit synchronous up-down counter and the next state after the clock pulse. So here we can see that the last valid state for our case was 1000, which means 8, and then the invalid one will be the next one, which is 9, and the binary number representations for that number is 1001. So that is invalid, and the recycle one will be 0000. So this is our recycle state. And if we go through this, we can see there are two numbers in Q1 and Q2 that needs no change. So we will not be changing this one, and so we will have to work according the Q0 and Q3 one. So the Q0 will be forcefully stable because it was the last valid state was 0, and the next state we are expecting is 0, Q0 for 0. So it will change actually. So it will be forcefully stable. We have to make it stable at 0, and the Q3 will be forcefully toggle because as we can see, the last valid one was 1, and then it was supposed to be 1, but we want it 0. So we need to toggle it. So this was the logic, and we have two formulas for forcefully stable and forcefully toggle, and after using that formula we actually get these equations where j naught and j3 will be changed, and the j1 and j2 will be the according to the regular rule. And these equations actually ensure that when the NG sensor is active, the counter moves to the next higher binary value, and when the exit sensor is active, it moves to the next lower binary value. So since the counter is synchronous, all state transition happen at the same clock edge, and these equations guarantee correct and these actually guarantee correctness and carry and borrow the operations actually. So this will be the end of our first question, and we will be moving forward to our next question now. So here we can see the number 2, and I'm not going to read the whole question. So basically it asks to design the circuit using 555 timer. So let's explain how I did it. Okay, so for timer 1 we will need a timer that actually keeps the display continuous and shows full. So as we know, to show something in continuous mode, we will need a timer monostable mode. In monostable mode, the timer will be in continuous mode, and for the timer 2 we will keep the timer 2 a stable mode, as we need the display to blink. Whenever it blinks, it will be in a stable mode, and because of using the stable, the display can oscillate or differ or blink, etc. So if we now talk about how I did the math, and this is my ID and the according alphabets for my ID, and these were given in the question paper. How do I calculate P? And this is my P value and the duty cycle from that value and the frequency from the value. Then I calculated the time period, and here now I actually need to calculate the high time and low time, and the formula for high time is d into t, and I did exactly that. And the low time formula is 1 minus d whole bracket into t. So basically I actually calculated the high time, which is actually the on time, and the low time, which is actually the off time. So the on time in my case is 58.33 millisecond, and the off time in my case is 25 millisecond. And then I actually justified it with the usual the standard equation of high time and low time, which is here 0.693 into R1 plus R2 into C. So to justify that, and we actually we were given three capacitors, which were 50 microfarad, 250 microfarad and 470 microfarad, and we calculated the resistors that were needed from these capacitors value. So this is the value for 50 farad, and here's the value for 250 farad, and in here the value for 475. And lastly we were asked which capacitor should we use. So in my case, I 250 farad microfarad capacitor gives us the mid-range resistors, which mid-range we actually consider 140 to 200 ohm. So it was 250 microfarad in my case. Then the next process was pretty much easier. We just designed the 555 timer using those resistor values and capacitor value. Then another thing is, to show something continuously, the duty cycle needs to be 100% or close to 100%. So only then we can take the output. The output won't be affected or actually continue showing the text or anything like that. So as for the continuous high output, the t high time needs to be equal to the time period we got earlier, and the load time should be 0. And here's the formula. We again then we actually calculated the high time for this case, and the resistors value, the R2 was 0 and load time was 0, and R1 we got 481 ohm. Then we designed the circuit again, and this is for the monostable mode. And with this, our second question is completed, and now I'm going to talk about the third question here. Let's move forward. So the question 3 actually asks to design FSM, and I'm going to talk about it now. Let's move forward. Okay, so let me talk about the purpose of the FSM. The purpose of FSM is to generate precise timing control for outputs A and B. So I designed a finite state machine. The finite state machine outputs A for high time milliseconds and the B for low time milliseconds, which is TH and TL. And here in my case TH and TL is 58.33 millisecond and 25 millisecond, but the question constraint was if TH and TL is greater than 4, then we will be replacing both of them with 4 milliseconds. So the A and B will be 4 and total cycle will be 8. Then what does it mean actually? So it means the clock period is 1 millisecond, so each state represents 1 millisecond, and I used multiple states to represent the on and off durations. If TH or TL exceeded 4 milliseconds, I actually limited them to 4 milliseconds as instructed. Now let's explain the state diagram. uh, Here's my state diagram. The state diagram, each state represents a timing setup, and each transition occurs on a clock pulse. So the FSM starts with states where output A is active, and then transitions to states where output B is active. So basically this is what FSM state diagram does. Then if we talk about the state table clearly shows the present state, next state, and corresponding output values. So from the table it is easy to understand how the FSM controls output A and B over time, and it is actually pretty much closer to the previous state table that we seen in question 1. There's some minor changes here, but almost the same as that one. Then there is this HDL Verilog code, which I have written to generate these outputs. And with this, our question 3 is covered. And now if we talk about the question 4, uh, it actually asked the limitations or the modifications I can make in this system. So I have talked about this. This is all very theoretical, but if I point out the main of the most important of them, this will be the limitations of question 1, and that was counting the range. The system uses a 4-bit up-down counter which can count only up to 15. So there's a limitation in range here. Then there's another limitation, which is no overflow or underflow protection. I didn't use actually any overflow or underflow protection here, so there's this limitation. Then if we talk about the limitations of part 2, here are some theoretical limitations that I talked about. Most important one of them is the 5-5 timer doesn't have a built-in enable pin, so we will actually manually do that. The output frequency and duty cycle depend on the resistor and capacitor value, so we will be needing the resistors and the capacitors here, and using multiple 555 timers and discrete logic becomes insufficient and complex when the system's size increases. So there's a connection with the system size or the circuit size, so there's this limitation. And there's one another, I'm not going to read it. And if we talk about the modifications, we can make some modifications to make our system better, and some of them are using LCD or LED matrix display instead of 7-segment display, because 7-segment display only shows up to 7 up to 9. So this is the limitation. We can modify that, and adding a debouncing and validation logic, or using advanced sensors or such as IR pairs or camera based detection to reduce counting errors. We can do that, and the impact of these modifications will be increased scalability, then improved accuracy, higher complexity, or yes, there will be higher complexity and cost, and better performance and flexibility will be there. So this was all. In conclusion, this project or system actually allowed me to apply digital logic or concepts such as counters, timers, FSMs, and then the control logic to solve the real world engineering problems. So basically the assignment was useful in its own way. The system satisfied the given requirements and followed outcome-based educational principles. So this was all from me, and I'm going to take my leave now. Assalamu alaikum. Be safe.